The equivalence you found out above is called the Norton theorem we are introducing now. For any one-port network with independent sources, linear resistors, and linear dependent sources, it can be equivalently replaced with a parallel connection of an independent current source whose value is the short circuit current of the network and the conductor whose value is the input conductance seen from the port. The Norton circuit is equivalent to the former circuit, and the Thevenin circuit is equivalent to the former circuit too. Obviously, the Thevenin circuit is equivalent to the Norton circuit. According to the equivalent relationship between the actual voltage sources and the actual current sources, you can see that UOC is equal to ISC times Ri, and GI is equal to the reciprocal of Ri. Because of the equivalent relationship between the actual voltage sources and the actual current sources, we needn't remember the Norton theorem. As long as we have the Thevenin equivalence, we can draw the Norton equivalence without difficulty. Besides, by comparison of the Thevenin theorem and the Norton theorem, it can provide us another method for solving the input resistance. Please look at the Thevenin circuit. What's its short circuit current if terminal A and B is short? ISC is equal to UOC over Ri. The short circuit current is the same in the Norton circuit. Since they are equivalent, so the short circuit current is ISC. By comparison, we get a conclusion that the input resistance Ri can be acquired by the open circuit voltage UOC over the short circuit ISC. So you can see U to the I method or I to the U method, or calculating the open circuit voltage and the short circuit current, and then the ratio can also get the input resistance. Next, we have two exercises to explain the applications of the Thevenin theorem. Please look at the exercise 1. We need to find the current I. There are several methods to solve the exercise. You may assume many branch variables and write out many equations according to the KCL and KVL. You may also use the node voltage method. Suppose this is a reference node and this node voltage is known, and you should solve the linear algebraic equation with two variables. You may also use the loop current method. There are three meshes. You should solve the linear algebraic equations with three variables. These methods are all available. But Rx has two values, 1.2 ohm and 5.2 ohms, which means the coefficient matrix of the two-node voltage linear algebraic equations will be changed, and the coefficient matrix of the three mesh currents linear algebraic equations will be changed too. The calculations are too complicated to get the results from the two situations. If we use the Thevenin theorem to solve the question, the solution will be simplified. So how to use the Thevenin theorem? You should see outside from terminals A and B and draw the Thevenin equivalent circuit. In other words, you can pull Rx out and see the Thevenin equivalent circuit between the terminals. You should find the open circuit voltage first and then solve the input resistance. Well, this is a circuit seen from terminals A and B. The voltage across this resistor is 4 volts. The voltage across this resistor is 6 volts. According to the KVL, UOC equals 6 minus 4 equals 2 volts. Then we solve the input resistance. Don't forget to set all the independent sources inside the network to be deactivated. For the ideal independent voltage source, deactivation means it's short. What's the input resistance seen from terminals A and B? It's the serial connection of two parallel connections of 4 ohms and 6 ohms. The input resistance is 4.8 ohms. Thus, we get the corresponding Thevenin equivalent circuit, including 2 volts voltage source, 4.8 ohms resistor, and the resistor Rx. We need to emphasize the relativity of the equivalence again. Only the branch variables of Rx is unchanged between the two circuits, and other branch variables are changed. So, the voltage and the current of Rx branch in the right circuit is the same as that in the left circuit. Well, the circuit I equals 2 over 4.8 plus Rx. When Rx is 1.2 ohm, the corresponding current is 0.333 ampere. When Rx is 5.2 ohms, the corresponding current is 0.2 ampere. You can see, after we get the Thevenin equivalent circuit, it's convenient for solving some branch voltage and current when its branch resistance is changed. This is the first application of the Thevenin theorem.